All right, let's take roll. Okay, let me all right, answer to your names, please. Bartram, Blair, here. Donnelly. If I'm not mistaken, Donnelly is available online. Elwell, Levengood, Miller. Miller is here. Sheffield, here. Sullivan, Phyllis. All right. So we're going to continue our discussion of gases. And in particular, we'll be discussing some other laws. Again, this should be a bit of a review for you guys. So we talked about Boyle's law earlier. So the next law we're going to discuss is Avogadro's law, which describes the relationship between the moles of a gas and the volume. All right. And in words, this is what the law says. At a fixed temperature and pressure, the volume of a gas is directly proportional to the number of moles or the number of molecules of gas, because of course, moles and molecules are directly related to each other. For every 1 mole of a gas, the number of molecules is a fixed number, 6.02 times 10 to the 23, all right? So that's basically what Avogadro's law is saying. So this is one way of expressing it. The volume is directly proportional to the number of moles, or the volume is equal to a constant times the number of moles, or when this is rearranged, you end up with the volume divided by the number of moles equal to a constant. And yet there's a third way that we can express it. I'm just going to squeeze it up here. It's V1 over N1 is equal to V2 over N2, all right? So that's basically the relationship between the volume of a gas and the number of moles. Please note that in order for this law to hold, the temperature and the pressure must be the same, all right? Constant, exactly, all right? And that is what leads us to the next point here, as you can see on the screen, where it talks about what is called the standard temperature and pressure, because in order for you to make meaningful comparisons between, let's say, different gases, especially when you're looking at stoichiometry, you have to take into account the temperature and pressure. So if you decide on a fixed temperature and pressure to be standard values, then we can make those kind of comparisons without, any major issues. So the powers that be decided that the standard temperature would be 0 degrees Celsius and the standard pressure would be 1 atmosphere. And of course, 0 degrees Celsius is the same thing as 273 Kelvin, all right? So whenever you see a question saying STP condition, standard temperature or pressure, then you should immediately understand that they're talking about those values I just mentioned, temperature being 273 Kelvin and the pressure being equal to 1 atmosphere. This leads us now to another concept which you should have met before, this concept of the molar volume, right? The molar volume, by definition, is the volume occupied by 1 mole of a gas, all right? That's the definition of the molar volume. And it turns out that under STP conditions, the molar volume has a value which is the same for all gases, and that is equal to 22.4 liters. So every 1 mole of any gas under STP conditions will occupy a volume of 22.4 liters, all right? Okay, so that is as far as Avogadro's law is concerned. The next law we're going to talk about here is what is called Gay-Lussac's law. And basically this law describes the relationship between temperature and pressure. And let me see if I can bring it up here. It says here, at a fixed volume and moles of gas, the pressure of a gas is directly proportional to the temperature expressed in Kelvin. So in other words, we can write it mathematically this way. The pressure is directly proportional to the temperature, or the pressure is equal to a constant multiplied by the temperature, or the pressure divided by the temperature is equal to a constant. All right, whoops, sorry. Remember now, in this particular case, the temperature has to be expressed in Kelvin. All right, now the pressure units can be expressed in pretty much any other units. And let me just say here, there's another way that we can express this law. P1 over T1 is equal to P2 over T2. All right, so the temperature must be expressed in Kelvin. The pressure units P1 and P2 can be anything, any pressure unit, any appropriate pressure unit like atmospheres, millimeters, mercury, torr, as long as they're the same on both sides. All right. So that's Gay-Lussac's law, which describes the relationship between pressure and temperature. And please note also that this is true at a fixed volume and moles of gas, the relationship that is. All right. Okay. So based on what we have covered so far, we should be able to do questions such as this one right here. This question says, let me get my black ink ready. This question says, calculate the volume occupied by 4.11 kilograms of methane, and it gives you the formula of methane under STP conditions. So basically, they gave you 4.11 kilograms of methane, and they're asking for the volume, presumably in liters, of methane at STP.
So that'd be 0 degrees Celsius in 1 atmosphere.
Exactly, exactly. Now, what I would do, of course, is start off with what we're given. And the first thing I would do is convert the 4.11 kilograms to grams. And by now, we should all know how to do that. You multiply by the appropriate conversion factor. And then the next step would be to find out the moles of methane. So, of course, we have to go to the periodic table, and we have to add up the molar masses of carbon, which is 12.01 plus 4 times 1.008. So according to my calculations, this works out to be 16.13 grams of methane, and 1 mole of methane would go above. Now, here is where the STP comes in, because remember we said that for any gas, the volume occupied by 1 mole of any gas, including methane, would be 22.4 liters, right? So we can represent that in this conversion factor, where I would put 1 mole of methane down here below and 22.4 liters of methane above. And that's it. So that's the setup. And then we have to do the number crunching. Divided by 16.13 times 22.4. And when I round this off to what, 3 sig figs, I got 5.71 times 10 to the 3 liters of methane. And that's how that is done. All right. Any questions about this? Any questions? Any questions? All right. So moving along. So far, we have talked about the relationship between pressure and volume, which is described by the Boyle's law, volume and number of moles, which is described by Avogadro's law, and the volume and temperature, which is the Gay-Lussac's law. If you combine these laws, right, you're going to end up with this expression here. We call this the combined gas law. In most textbooks, they do not include the number of moles because we are assuming that the number of moles will be the same, but it's still appropriate to have the number of moles there still, so it doesn't matter. But basically, this is what happens when all the different variables change as you go from, one set of conditions to another, right? And therefore, you can use this equation to solve for any one of these terms if you know the other 7 terms, all right? So if you want to find V2, let's say you want to find V2 here, you'd have to do some algebraic manipulation to get V2 by itself and all the other variables on the left side, all right? So that's basically the combined gas law. Any questions about this? Any questions? Okay, so let's look at this example. So this question says you have a flask which contains oxygen, one on the left at STP and the one on the right at 100 degrees Celsius. What is the pressure of the gas at 100 degrees Celsius? So the combined gas law would come into play. P1 V1 over N1 T1 equals to P2 V2 over N2 T2. Now, fortunately for us, we can simplify this equation here. Why? For one, it's the same flask at the start as we have at the end here, right? So therefore, we know that V1 will be equal to V2. It's the same flask. So therefore, these two will cancel out. All right. What else? The number of moles are also going to remain the same because we're assuming that no gas is escaping. So N1 and N2 will cancel out. So this equation simplifies the P1 over T1 is equal to P2 over T2, right? What the question is asking for is P2. So therefore, P2 would be equal to P1 T2 divided by T1. So it's all a matter now of putting the numbers in. So we have to identify the different terms in this equation. Now, remember the question says the one on the left is at STP, right? So in this case here, what that tells you is that P1 is equal to 1 atmospheres. I'm going to put 1.00 atmospheres here. And T1 is equal to 273 Kelvin because those are the STP conditions. All right. And here it says that the second temperature, T2, which must be expressed in Kelvin. So we add 273 to that. So that gives us 373 Kelvin. All right. So we put all those numbers into this equation right here. So P1, as I said before, is 1.00 atmospheres times T2, which is 373 Kelvin, all divided by T1, which is 273 Kelvin. And basically it's 373 divided by 273. Well, I got 1.37 when rounded off to 3 sig figs. So the answer becomes 1.37 atmospheres because the Kelvin units will cancel out. All right, so that's how that is done. Okay, any questions about this particular example? Any questions? Okay, moving along. Oh, there's a question being asked here. I just saw it popping up. What pressure would be exerted? Okay, so let me remove all these markings here. This question says, what pressure would be exerted if this vessel was transferred to an oil bath at 200 degrees Celsius? Well, that's easy because you just change the temperature, right? I don't think I need to do that for you guys. All you have to do is use the same equation. The equation that we were using is P2. P2 is equal to P1 T2 over T1. So all we have to do is use the same numbers, excepting that T2 is going to be 200 degrees, which you have to convert to Kelvin. And that's it. All right. So I leave that for you guys to try on your own. All right. So we talked about all these laws, right? And you'll notice that in each of these cases, in the case of each law, there are two potential variables that are held fixed, right? In the case of Boyle's law, the number of moles and temperature would be constant. In the case of Charles' law, the number of moles and pressure would be constant. In the case of Gay-Lussac's law, the number of moles and volume will be constant. And finally, in the case of Avogadro's law, the pressure and temperature will be constant, right? So the question now becomes, what if everything changes? Well, it goes back to the equation that we showed you before, which is the combined gas law. And when we take any particular pressure, volume, number of moles, and temperature and place it into that arrangement, you end up with this equation here, which turns out to be a constant, and that constant is called the molar gas constant. So basically, when you do the calculation of the molar gas constant, that's the value you're going to get. 0.082, we're going to round off for all purposes to 3 sig figs as far as R is concerned. So 0.0821 would be the numerical value. And please notice the combination of units right here. It's liters, atmospheres divided by mole Kelvin, which reflects the arrangement of the terms in this equation. The pressure unit, the volume unit, the moles and temperature down here as a denominator, right? Another way of expressing it, which is probably the most popular way of expressing this relationship, is this equation right here. PV is equal to nRT, and this is called the ideal gas equation. And this basically shows the relationship between these variables for an ideal gas. And later on, we're going to talk about the difference between what we call an ideal gas and a real gas, right? And there are some differences that we will have to take into account when you're going from an ideal situation to a real situation. Okay, so some things about this ideal gas equation. With respect to this value of R, the pressure must be expressed in atmospheres, the volume must be expressed in liters, N must be expressed, of course, in moles, and the temperature must be expressed in Kelvin, right? Now, there are other values of R which would be dependent on some other units. So let me move on to the next slide. So this R value here is the one that we just saw, and that is true when the pressure is in atmospheres, the temperature in Kelvin, volume is in liters, and of course, mole units would be involved. However, if you just make a change from atmospheres to torr, then you get a different numerical value of R with a corresponding change in the units right here, all right? I don't anticipate us using this value too much, all right? Now, there's another value of R which you will meet later on in this chapter, and that is this value of R here, which is the value of R if the pressure is expressed in pascals and the volume is expressed in meters cubed, all right? And that value of R here is 8.31 joules per mole Kelvin, all right? So we're going to meet that later on when we get to a discussion of diffusion, all right? That's towards the end of this chapter, all right?
That's on the purple stuff.
Oh, yes, that's also, yeah, you should find it in that table there. Yeah, okay. So in most of the cases in this chapter, you'll be using this R, but I'm going to point out where this R is going to be used, all right? Because that's kind of important when you get to that particular topic, all right? Okay, so some more examples. What is the pressure exerted by 0.508 moles of oxygen in a 15.0 liter container at 303 Kelvin? So the equation which readily comes to mind would be PV is equal to nRT equation, right? So the question is asking for P. So P would be equal to nRT divided by the volume. So they gave you N, which is 0.508 moles, times R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 303 Kelvin, and then I will divide all of that by the volume, which is 15.0 liters, all right? So that's a setup, and of course, you'll notice that the mole units will cancel out, the Kelvin will cancel out, the liter units will cancel out, so the final unit you're going to end up with is atmospheres. So let's do the number crunching, 0.508 times 0.0821 times 303 divided by 15. And according to my calculation, and of course, again, please let me know if I'm on the wrong path, but I got 0.842 atmospheres, all right? So that's it. So that's a pretty straightforward question because they gave you pretty much everything you need. If you know the equation, you know, everything you need to plug into the equation to get the final answer. Okay, any questions? I don't think there are any questions about this one. All right. All right, so let's move on now to the next one. Now, this one is a bit different because for one, they're asking for the volume of the gas. For two, they gave you the mass. For three, they gave you the formula, and they gave you the pressure in torr and the temperature in Celsius. So obviously, there's some unit conversions that you'd have to engage in order to solve this problem. So again, the equation we're starting off with is PV is equal to nRT. So what the question is asking for in this case is the volume, which is equal to nRT divided by P. So let's see how we can deal with that. The first thing we need to do is determine the moles. They did not give us the moles. They gave us instead the grams, and they gave us the formula, which is important because if you know the formula, you can calculate the molar mass. So let me do that right now. So the molar mass of ethane is 2 times 12.01 plus 6 times 1.008. And according to my calculation, the molar mass is, I got 30, okay, 0.09 I got. All right. So the volume would be equal to the number of moles, which is 16.0 grams multiplied by 1 mole divided by the molar mass, which is 30.09 grams. All right. So what I've just calculated here is N. Then the next thing that follows that would be R, which is always 0.0821 liters atmospheres over mole Kelvin. And then we multiply by the temperature. Now they gave us the temperature in Celsius. So we add 273 plus 18, and that gives us the corresponding temperature in Kelvin. Whoops, 291 Kelvin. So that goes here, 291 Kelvin, all right? Then we get to the pressure. They gave us the pressure here as being equal to 720 torr. So we need to convert that to atmospheres. If you're going to use this value of R, where we have the atmosphere unit here, then we have to convert the torr units to atmospheres. And if you go to the chart, which gives you all the conversion factors, you'll see that 1 atmosphere is equal to 760 torr. All right, so that's the setup. And let me just show you how the units cancel out. The grams will cancel out here and here. The moles will cancel out here and here. Kelvin cancels out. Atmospheres cancels out. The torrs cancel out. So the only unit remaining, which is liters, which comes as no surprise because you're actually calculating for the volume. So 16 divided by 30.09 times 0.0821 times 291 equals, and then divide by 720 times, not times, but divided by 760. Okay, so correct me if I'm wrong, but what I have here in front of me is 13. Well, actually, I'll round out to 2 sig figs because of the 720 here. So it would just simply be 13, and the units here would be liters. All right, so that's basically what I got. All right. Okay, any questions about this example? Any questions? Any questions? All righty, let's move on. Okay, so, okay, let's talk about some other useful things we can do with the ideal gas equation. We can use it to experimentally determine the molar mass of a gas, all right? So this is based on the ideal gas equation. And what we're going to do in order to examine how this is done, we're going to use, in this particular case, uppercase M to represent the molar mass and lowercase m to represent the mass in grams, right? So if you understand the relationship between these two, you'll notice that the molar mass, which is by definition the mass in grams per moles, would be equal to the mass in grams divided by the moles. So uppercase M will be equal to lowercase m divided by n, right? And therefore we can algebraically rearrange this equation here to solve for n, and n would be equal to lowercase m divided by uppercase m, right? Now, the ideal gas equation can be rearranged itself to get n equals to PV over RT. So what that means is that these two terms will be equal to each other, right? So if we set this to be equal to this, we're going to end up with this relationship right here, right? And then we can rearrange this equation to solve for uppercase m. And when we do that, this is what we end up with, right? So basically, this equation is what you can use to determine the molar mass of a gas. If you know the mass of the gas, if you know the temperature, the pressure, and the volume, then basically we just plug those numbers into that equation, and that will give us the molar mass of the gas. And this is, of course, based on the ideal gas equation. All right. Any questions about this? Any questions about how this equation is derived? Any question? Oh, okay. Give me some time to rest my voice for a quick minute. All right, so I think the next slide is an example based on this very equation. So the question gives you, in this case, the mass of the gas, the volume of the gas, the pressure, and the temperature. And what the question is asking for is the molar mass. Well, it says molecular mass, but remember, molecular mass and molar mass are numerically the same. The only difference would be the units, right? So all we have to do is find the molar mass and then switch the units. Okay, so the equation that I just showed you is molar mass is equal to mRT over PV. And by the way, I think this equation is also in the packet that I've posted in Canvas, I think. In any case, so we put the numbers in. In the case of the mass, that is 0.550 grams times R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 289 Kelvin. And then we divide that by the pressure, which is 0.968 atmospheres. Keep messing up with this thing. Reading. I hate Reading. Times the volume. What's the volume? 0.200 liters. So that's a setup. The gram units will remain. Why did I cancel it? Okay, so the gram units will remain. The liters will cancel out. The Kelvin will cancel out. The atmospheres will cancel out. So the final units would be grams per mole, which would be the units of molar mass. So we do the number crunching, 0.550 times 0.0821 times 289 divided by 0.968 divided by 0.2. And according to my calculation, the answer I got is 67.4 grams per mole. So the final answer is that the molecular mass is 67.4 AMU. All right? Because the question, remember, is asking for the molecular mass. Okay, any questions about this particular example? Any questions? Any questions? All right. Next example. Similar question, actually, but of course, a bit more challenging because they gave you the temperature in Celsius, they gave you the pressure in torr, they gave you the volume in milliliters. Well, this still works out for us in terms of simplicity. But the question is asking again for the molecular mass, which is numerically the same thing as the molar mass, which is mRT over PV. So we put the numbers in. So we start off with the mass in grams, which is 0.523 grams times R, which is 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 100 degrees. We convert that to Kelvin, that becomes 373 Kelvin. And then we divide that by the pressure. Now, in this case, they gave us the pressure being equal to 755 torr. We have to convert that to atmospheres. So we multiply by this conversion factor here. And then finally, as far as the volume is concerned, they gave us the volume being equal to 185 mils. We have to convert that to liters. So you're going to get 1 liter over 1,000 mils. And that's the setup, right? So therefore, in terms of units canceling, let's see here. Let's start out with the Kelvin that got to go. The liters will cancel out as well. The milliliters will cancel out. The atmospheres will cancel out. Oh, shoot, sorry. This here should be torr. This torr will cancel out with this torr. This atmospheres will cancel out with that atmospheres. So the only units that will remain is grams per mole. So let me do this number crunching here, 0.523 times 0.0821 times 373 divided by 755 divided by 760 divided by 0.185. Okay, so again, please correct me if I'm wrong, but what I got here is 87.1 grams per mole. So therefore, again, we can say that the molecular mass is equal to 87.1 AMU. All right, and that's how that is done. Okay, any questions about this example? Any questions? Any questions? All right, moving along. Okay, another application of the ideal gas law is that we can use it to calculate the density of a gas. All right. Now, of course, densities are not, how should I put this? Densities of gases are not held to the same, for lack of a better word, value as the density of solids and liquids, right? And that's because the volumes of gases can change, I mean, like it can vary real widely. Like, you know, you can literally double the volume or triple the volume or half the volume with ease compared to solids and liquids. So therefore, we do not use it as a physical constant as we would in the case of solids and liquids. But however, sometimes you need to calculate the density, and we can use it based on the ideal gas equation. In fact, we can use it based on this equation that we were just using, right? Now, this, of course, if you remember, we derived from the ideal gas equation, right? So we can rearrange it to get M over V on one side, and you get the other terms here. So M over V would be equal to, and by the way, this is lowercase m divided by V would be equal to uppercase MP divided by RT, right? And of course, you should recognize that M, lowercase m, over V is, by definition, the density, right? So therefore, this is the equation that we end up with. The density of a gas is equal to the molar mass times the pressure divided by R times the temperature, again, expressed in Kelvin, all right? And based on this relationship, we can see some interesting relationship between different terms. For example, we can see the relationship between the density and the pressure of a gas. Basically, what this equation tells us is that if the pressure increases, then the density of the gas increases, right? Or we can look at the relationship between the density of the gas and the molar mass, right? If you have two gases, one with a larger molar mass than the other, everything else is the same. The pressure and temperature are the same. Then based on that equation, we can conclude that the greater the molar mass, the greater the density. And then finally, we can see that there's an inverse relationship between the density of the gas and the temperature, right? As you increase the temperature, then the density decreases and vice versa. You have an inverse relationship between those two. Okay, and one more thing I want to make mention of before I leave this particular slide, and that is if we use all the appropriate units that we talked about before, molar mass is in grams per mole, pressure is in atmospheres, T is in Kelvin, and R would be expressed in the units that I indicated earlier, then you'll see that the density units would be grams per liter, right? And that is typically the units that we use to express density. Because again, gases typically have relatively large volume, you know, compared to solids and liquids of the same mass, all right? Okay, so let's look at this example. This question says, what's the density of methane gas in grams per liter at 25 degrees Celsius and 0.978 atmospheres? Density, according to the formula we just saw, is MP divided by RT. So M would be the molar mass of methane, which we calculated earlier. Can you remind me what the molar mass of methane from a previous example, what it was? I don't want to go through and calculate it again. Oh, 16 point something.
Well, that, I put a methane, but.
Mhm. CH4,
16.13.
13, okay. Grams per mole times the pressure, which is 0.978 atmospheres, divided by R, which is always 0.0821 liters atmospheres over mole Kelvin, times the temperature, which is 25 degrees. So you have to convert 25 degrees to Kelvin. And that gives you 298 Kelvin right here. And then we do the appropriate unit cancellation. Atmospheres will go, moles will go, Kelvin will go, and we're left with grams per liter as your final unit. So 16.13 times 0.978 divided by 0.0821 divided by 298. And according to my calculations, when rounded off to 3 sig figs, you're going to end up with 0.645. That's what I got. And that would be the density of methane gas under those conditions. Okay, any questions? Any questions about this one? All right, here's another example. Now, this question says, under what pressure? So this question is asking for P, right? Must oxygen be maintained at 25 degrees Celsius to have a density of 1.50 grams liters? So what I would do in this particular case is use the same formula, right? But I would rearrange it to solve for this, right? So if I do that, I'm going to end up with P being equal to D times R divided by times T divided by M. So P in this case would be the density, which is 1.50 grams per liter, times R, which is 0.0821 liters atmospheres over mole Kelvin, times T, which is again 298 Kelvin, divided by the molar mass. So what's the molar mass of oxygen? 2 times 16. So that would be 32.00 grams per mole. And that's it. That's the setup. So 1.5 times 0.0821 times 298, and then divide by 32. And according to my calculations, this works out to be equal to 1.15. And the units here would be, well, let me show you how the units cancel out. The grams here will go, I'm sorry, the grams will go, the moles will go, the Kelvin will go, the liters would go. So the only unit left would be atmospheres. And that's how that is done. All right. Okay, any questions about this one? Any questions? Okay, so based on what we have covered here, let me see, let me go to, where is it? So this is assignment number 5. And okay, so let me, so if I remember correctly, we got as far as question number 2, right?
Yep. All
right, so basically from what we've done so far, you should be able to do questions 3, 4, 5, 6, 7. Okay, so from 3 to 7. All right. So for the time that we have left here, well, maybe you should, well, yeah, for the time that we have left here, you should try those questions. I'm here if you have any questions you want to ask. And for you, let me see who's out there in Zoom. Okay, so Sullivan, oh, somebody left. Okay. Anyway, you guys out there, same thing. You can attempt question 3 through 7. And if you have any questions, I'm here to help. What's up? Okay, so for number 3, they gave you the pressure of the gas. Okay, so in this case here, they gave you the initial pressure. Where's my pencil? They gave you the initial volume, so I'll call that V1. This is the initial pressure, I'll call that P1. And this is V2, right? So basically what the question is asking for is P2. So the equation that should come to mind is P1 V1 is equal to P2 V2, right? And then you just put the numbers in and solve for what the question is asking for. Excuse me.
You can work for reaching over the atmosphere.
Let me see. Question number 3. Well, they didn't specify, so you can leave it in Tor if you. So,
That's a really
Hmm?
the atmosphere.
well, I mean, if you use Tor for P1, then when you do the calculation for P2, you're going to get in Tor, right? So you can leave it in Tor because the question didn't specify what units.
Sounds good.
Hmm.
Thank you.
Yes, sir.
So for number 6. We just use,
Okay, so for number 6,
we just switched out to.
they gave you pressure. Okay, so they gave you the initial pressure, the initial volume, and initial temperature. And the question is, what will be the temperature of the gas if you change the pressure to 278? So based on what I see here, the volume doesn't change. The question didn't say that the volume will change. The question only said that the initial pressure is that, the initial temperature is that, and the final pressure is 278 millimeters mercury, right? So this is P1, this is T1, right? And this is P2. So the equation that comes to mind is P1 over T1 is equal to P2 over T2. And what the question is asking for you to do is solve for T2. Right? Yes, sir.
I just want to double check, 'cause this is a pretty large number.
Oh, no, that's too large. Okay, let me see what you did here. Did you calculate the molar mass of SO3?
Should be 96.
Let me cheat a little. That should be 80 point, yeah, 80.06. So you should have 80.06 here times the pressure, which is 0.96, and then divide that by 0.0821, divide by, okay, 8. That's what I got, 30.3. And the units will be grams per liter.
We're at 96.
Yeah, you probably zigged what you should have zagged when you were doing your calculating. What did I get? I got 3.04. Yeah, but they should be grams over liters, not right. Yes, sir.
Report B. I don't want to go with Jason.
Okay, so, oh, well, you could use a different form of a pencil of this equation. Because the question gave you the density. So what I would do is I would use D is equal to MP over RT.
All right, I just don't know how that's.
And then find M.
We find them first and then. Okay.
Well, find M by plugging in the other numbers. Yeah. All right, folks, you can finish up on that over the weekend. Let me just say that I've also extended the deadline for assignment number 4 to Monday. All right. So you can drop it off in my mailbox or you can upload it into Canvas if you so choose. And make sure that if you do so in Canvas, make sure it's in a PDF form. All right, so that's it, folks. See you guys next Tuesday. You too.
Agree with you.
You too.